Good morning, everyone. We are going to see today in today lectures the Bravais Lattice. Last lecture we have studied about the different type of crystal system. There are 7 crystal systems are allowed. Any crystal system or any solid crystalline solid, you can put one type of crystals into one type of crystal system. That is the thing we have discussed. And those 7 type of crystal system we have discussed about that the examples as well as the how we can define the lattice parameter. According to lattice parameter, how we can categorize the 7 type of crystal system we have discussed. In this today lecture, what we are going to analyze means the Bravais lattice. In the 7 type of crystal system, there are sub crystal system also exist. In general, in Bravais lattice, you can define for the 2 dimension, you can define it for the 3 dimension. These two crystal system you can define with some numbers, some different number of crystal system. So any solid in nature occurs, you can put in one type of the crystalline system, but that solid should be the crystalline solid. We are not anything discussed here about the amorphous solid. We are discussing everything about the crystalline solid. So we are going to discuss now the Bravais lattice. In Bravais lattice, if you look at the 2 dimension, how many types of exist? If you are asking that question, there are 5 types are exist. So in 2 dimension, only the 5 Bravais lattice exist that we anyway we are going to discuss. We can ask suddenly another question: how many types of Bravais lattice exist in 3 dimension? If you're asking this question, the Bravais lattice showed that there are only 14 possible crystal lattice in 3 dimension. Not more than that, not less than that. Any crystals in 3 dimensional solids, you can put into this 14 type of Bravais lattice. If it is 2 dimension, suppose if you are making crystal like sheet kind of crystal, that 2D crystals, you can put into that 5 Bravais lattice. Example, the 2D crystal, you can say the best example. If you are taking that carbon sheets, what is the thing? If you are look at that, suppose if you are look at your pencil, there is an hexagonal carbon. One of the carbon allotrope structure will be there. That is a hexagonal structure. It will be kind of sheet. So 2D crystal system. So this crystal system, if you look at, if it is 2 dimension, it is 5. If it is 4 dimension, it is 14. Hence, these 14 types of space lattice in 3 dimension known as the Bravais lattice. If it is in 2 dimension, that is the 5. So in general, the Bravais lattice 2D is 5, in 3D is 14. That is a conclusion you can give. Anyway, with that we are going to discuss in detail in the next section. The lattice can be primitive or non-primitive. We can ask one question: what is a primitive lattice? What is a non-primitive lattice? This is a question now we are going to answer. Here we are going to discuss what is a primitive lattice. That is the question we need to answer. A primitive cell is the simplest type of unit cell which contains only one lattice point per unit cell. Even if it is 2 dimension, it is having one more unit cell. If it is 3 dimension, it is having only one type of unit cell, the simplest type of unit cell which contain only one lattice point. Even 3D also it's a one point, 2D also one point, that we can call it's a primitive cell. What do you mean by only one point? We have like a 2D, we have like kind of some area. In 3D it's some kind of cube, but the cube is connected with the 8 point. The 2D, the area also connected with the, suppose if you are finding the square, it is connected with the 4 point. How you can define the lattice point per unit cube, per unit area? Only one lattice point, how we can define? Anyway, this is a question we are going to answer in the packing factor section. because in the packing factor we are going to in deep how you have to define the number of atoms per unit cell. That is the thing we are going to discuss in the packing factor section. Anyway, that's the thing we are not going to discuss here. Just we want to know the definition. What is a primitive cell? The primitive cell means that cell should have only one point. Otherwise you can say that primitive cell having only the corner atoms. Suppose if you are taking the cube, only the corner having the atom, then that cell we can call it a primitive cell. There are no more atom inside or at the face. There is nothing, no more atom. Only the corner if it is having an atom, we can call it a primitive cell. Example, if you are taking the 2D, the square lattice, the only the corners having the atom, we can say that is a primitive cell. So I am just here. I am drawing. Here, if you are just taking the square lattice, only the corner having the atom. There are no atom inside or at the edges. So you can say this is a primitive cell. Even in 3D, the simple cubic. Suppose if you are extending this structure like a simple cubic, this simple cubic having only the corner atoms. So there are no more atom inside or at the face. We can call this as a primitive cell. Example, if you look at simple cubic, the simple tetragonal in the 3D. In 2D, you can say the simplest the structure. It's the square. What is a non-primitive? The next question really you can ask, what is a non-primitive unit cell? That means the unit cell which contain more than one lattice points is called the non-primitive cell. That means it have an extra point inside or at the face or at the edges. So you can call that unit cell is a non-primitive unit cell. What is a non-primitive unit cell means? Suppose if this is a simple cubic, if it is face center cubic, like in cube there are 6 faces will be there. If all the faces are having the point, then that we can call the face center cubic cell. Then it is having more than one lattice point. Only the corner, if it is having the atom, then it have only one lattice point per unit cell. That is the thing we are going to discuss in the packing factor section. Right now, just understand. If the corner having only one atom, that we can call it's a primitive. If the face also having the atom or body center having the atom, then we can call it's a non-primitive cell. So anyway, the example, the body center cubic, face center cubic, hexagonal packing structure contain more than one lattice point per unit cell. We can call that is a non-primitive cell. Going to look at the two-dimensional Bravais lattice. Already we have told in two-dimensional Bravais lattice having only 5 type of crystal system or 5 type of the lattice structure. First one is the oblique lattice with A1 not equal to A2 and pi not equal to 90 degree. What is the pi? What is the A1, A2 if you are asking? Look at that picture. This is the oblique lattice. The A1, A2, here it is shown the A1, this vector shows A2, the magnitude of the vector A1 along the x direction, A2 along the maybe it's tilted, but it's other direction. The angle between these two is acute angle but not equal to 90 degree. We can call this type of lattice is oblique lattice. The smallest area for the oblique lattice, if you complete this structure, this will give the smallest area. The angle between these two vectors, this you can call it's a pi. If A1 here it is not equal to A2, it has to satisfy this condition and pi not equal to 90 degree. We can call this type of lattice is a oblique lattice. The next Bravais lattice in 2 dimension is a rectangular lattice with A1 not equal to A2 with pi equal to 90 degree. That means the angle between the two vector is equal to 90 degree. Look at the second picture. Here if you look at this second picture, here the A1, here it is here, A2, the length are different, that's why A1 not equal to A2 here. Then the angle between them is exactly right angle, 90 degree. So if you want the rectangular lattice, that means how here we have shown two vector only. If you want to complete this structure, then it will be looking like a rectangle. That's why we are calling this as a rectangular lattice. The third type of lattice is a face center rectangular lattice with A1 not equal to A2 and then pi equal to 90 degree. So if you look at the third picture, here A1 again two vector, the A2 here, A1 is here, these two length will be different, the angle between them exactly right angle to each other, face center rectangular, because it's a right rectangle, the two length are different. Face center means if you are completing this structure, exactly this rectangular structure having the only one lattice point at the center of the face. That's why we are calling this is a face center rectangular lattice. The length are different. The angle between the two vector is 90 degree. The next one, if you look at, that is a hexagonal lattice with A1 is equal to A2. The angle between the two vector is 120 degree. Look at that fourth one. Here the A1, the distance between this vector, these two lattice point is equal to A1. The next lattice point, this is a A2. The angle, if you are measuring between these two vector, this angle it would be 120 degree. This is a hexagonal lattice. But here, if you look at how we can understand it's a hexagon. Hexagon means we have to have a six side. You got to complete this structure. See, draw it here, draw it here, draw it here, draw it here. There are six faces, then one center atom. This is actually the hexagonal lattice. So yeah, that is true, but the angle between the two vector is 120. Suppose if this is not equal to 120, then we have one more answer. Suppose if the angle is not 120 degree between these two vector, then it will be again oblique lattice. It will fall within this category, the first category. If it is exactly 120 the angle, then you can complete the hexagon structure. This is the fourth type of lattice in the Bravais two-dimensional Bravais lattice. Now the last one is square lattice. For the square lattice, A1 equal to A2, the angle between the two vector is 90 degree. Look at the last diagram. The x distance as well as the y distance, they are equal. The angle between them equal to 90 degree. You can just complete this structure to see the perfect square. You can repeat this structure in the x as well as the y direction to obtain the any crystal lattice in two dimensions. See here, this structure will repeat here, 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 here. Same way the face center here, rectangular. Same way the hexagonal structure also will be repeat. Same way the square lattice also will repeat. Oh, so any lattice structure in two dimension can fall within this phi structure, not more than this phi. You can just tell, oh, if this is a 2D crystal structure, this is you can just take the diagram, then you can draw the picture, then you can see it will be in one of the this one of the lattice structure, either oblique or rectangular or face center rectangular or hexagon or square lattice. Definitely you can find it. So this is a two-dimensional Bravais lattice. Now we are ready to discuss the three dimension. Before that, I want to tell one thing. In two dimension, we need two lattice parameter, that means two axial length, only one angle. But in three dimension, we need three axial vector or three the axial length, three angles. There we need six lattice parameter to define the crystal structure in three dimension. But in two dimension, we need only three lattice parameter, two axial length, one angle. Are taking the three-dimensional Bravais lattice, there are 14 types is exist. Just to look at the table, it will tells us. If you are taking the cubical structure, there are three cubical structure. One is simple cubic, body center, and then face center. If you are taking the tetragonal, there are only two: the simple tetragonal, body center tetragonal. If you are taking the orthorhombic, there are four types. One is simple, the base center, body center, face center. Base center is different from the face center. If you are taking the monoclinic system, there are two types. One is simple monoclinic, next one is the base center monoclinic. If you are taking the triclinic, it is only one, the simple. The next one, robohedral or trigonal, if you are taking only one, that is also simple. If you are taking the hexagonal, that is also only one. If I just to sum this type of crystal structure, 3 plus 2, 5 plus 4, 9 plus 2, 11, 12, 13, 14. The total number is 14. So that we have studied the crystal system, only the 7 crystal system. These are the 7 crystal system. But if you are look at the Bravais lattice, it is equal to the 14 Bravais lattice. One by one, we are going to discuss now. What is a simple? What is a body center? What is a face center? What is a base center? This is the thing we are going to discuss now. The first thing we are going to see in the three-dimensional Bravais lattice is the cubical system. The cubical system, it is categorized by Bravais into three. One is a simple, body center, face center. Look at the first diagram. What do you mean by simple means? The simple means it is having only the corner lattice point. That means if you are taking any simple cubic lattice, only in the cubical structure is a unit cell in the simple cubic crystal system. That cubical structure, only the corners having the lattice point. That means only the corner in the realistic case, only the corner having the atoms. That's why we are calling it a simple. There are no more extra atom in this. If you have to see the body center, corners having the lattice points, there is one more lattice point at the center of the body. That's why it is called body centered. If you look at the face center, see here, corners having the atom. Additionally, the face also having the atom. How many faces means 6 faces. See here, this face have one atom. This is the second face. This is the third face. The third atom. This is the fourth face. Fourth. This is a front face. This is 5. That is a back space. That is 6. So extra 4 atoms are in the each face of the cubical structure. That's why we are calling it's a face center. So if you are taking the cubical structure, there are no more structure is allowed. Either it will be simple cubic or body center cubic or face center cubic. The next crystal Bravais lattice we are going to see in the 3D is that is tetragonal structure. We told tetragonal having the two structure in the table. So what are the third one means simple body center. There are no more tetragonal. So here, if you look at the first picture, the corner having the atom, because each corner having the atom, that's why it is called simple. If the corner only having the atom, we can call that is a simple. That's why it's a simple tetragonal. Here it will match the tetragonal lattice parameter. Tetragonal lattice parameter A equal to B equal to not equal to C. Alpha, beta, gamma equal to 90 degree. That's a tetragonal lattice parameter. It should satisfy that condition. If it is simple tetragonal, it is having only the corner atom. That is the thing we have to notice here. Body center means it is having additionally only the body corner having the atom. Additionally, at the center of the body there is one more lattice point. That's why we can call it a body center tetragonal. One can ask here. One can raise a question. Why, sir? There is no face center tetragonal. If you are drawing the face center tetragonal, it will fall some other crystal system. It may be the simple tetragonal. You can just rotate it, and then if you look at that face center tetragonal, it will be again simple tetragonal. Just you can try. Maybe I can the 3D structure I can show it here. Maybe the tetragonal only the two structures are allowed. Only simple tetragonal. Next one is a body center tetragonal. If you want to write the base center or face center tetragonal, it will either fall simple or some other crystal system. That's why we are not represent the face center as well as the base center. Only these two structure is allowed in the Bravais lattice. The next Bravais lattice in 3 dimension we are going to discuss, that is orthorhombic system. We told in the table orthorhombic system having 4 types of crystal lattice, that is simple, body center, face center, base center. Look at the simple means we know it's only the corner having the atom. Additionally, it has to satisfy the 6 lattice parameter condition for the orthorhombic. Then there is a body center. If you look at the orthorhombic, there is a center of the body having 1 atom, as well as face center. There are 6 faces, so it is having 6 atoms at the faces of the unit cell. That's why it's a face center orthorhombic. Then base center. Base means the top base, bottom base. It is having at the center only 1 atom. That's why it is called base center orthorhombic. Only the orthorhombic system having 4 types, all the 4 types of the Bravais lattice. The next Bravais lattice in 3D, that is a monoclinic system. The monoclinic, it's just a simple monoclinic, base center monoclinic. Monoclinic, it has to satisfy the 6 lattice parameter. That is just you have to follow the previous lecture. Simple monoclinic means it is having only the monoclinic system having the units will have the corner atom. That's why the simple monoclinic. In terms of lattice point, if you are speaking, the monoclinic crystal unit cell or having only the lattice point at its corner. Base center monoclinic, it is having corner at lattice points plus additionally the base center lattice point. Base center means the top as well as the bottom. These are the 2 bases. If this base is center having the atom, then we can call it a base center. Here it's a monoclinic. That's why we are calling it a base center monoclinic. Here, next crystal system we are going to discuss, that is a triclinic. Triclinic in the table already first I have shown only one Bravais lattice is allowed, that is a simple triclinic. You can't put base center triclinic, body center triclinic. Why we can't put means you can't repeat that structure. That is another problem. So this is a triclinic structure. It has to satisfy the 6 lattice parameter. That means already I have told in the previous section. Just you got to follow the previous lecture, lecture 3. So this triclinic, simple triclinic means it is the corner having only the lattice point. The triclinic unit cell having the lattice point at its corner. The next one is the robohedral or trigonal. It is also only one Bravais lattice is allowed, that is simple robohedral or trigonal. It has to satisfy the 6 lattice parameter condition. That means A equal to B equal to C, alpha equal to B equal to gamma, but not equal to 90 degree. Already I told. Additionally, it has only the corner atoms. So that's why it is called simple robohedral. Why we are not having the base center, body center, base center robohedral means if you are making that one, you can't repeat the structure or it will fall some other structure. Either it will fall to some other structure. That's why we can't make it. Only the simple robohedral is allowed here. Last Bravais lattice we are going to discuss, that is the hexagonal structure. The hexagonal structure also having the simple hexagonal. If you look at this picture is hexagon, but here actually, yeah, it is right, but there are 3 atoms exactly, suppose at the center, at this triangle center below it's a 1 point, then leave this triangle at this triangle at a center distance here 1 point, leave this triangle at this triangle below at center it is this, there are three more atoms here. Anyway, that anyway we are going to discuss while discussing the packing factor why we are calling simple tetragonal, because it is little bit difficult structure, but we got to make it like a base center face center, that is even it more difficult. You can't tell like in the simple cubic body center cubic you can't visualize like that, but that's why we are taken the hexagonal structure. It's a simple hexagonal, only one structure is allowed. So that means the corners are having the atom, additionally the top base bottom base also having at the center one atom. So can we call it's a hexagon base center hexagonal? No, it has it will have additionally three more atom at the center of the top as well as the bottom face. That's why it is called simple hexagonal. So it's this structure is closed pack structure that anyway we are going to discuss in the packing factor in the section. So only one type of crystal system, Bravais lattice, is allowed. That is a simple hexagonal. We can see it here. Now we have discussed the all type of Bravais lattice, allowed Bravais lattice in 3 dimension. We have shown in the table while starting this lecture. Now also I want to show here once again. Look at that cubic. It is having simple body center as well as a face center. Now we got the clear information why body center, why face center, why it's a simple. The tetragonal 2 simple body center, the orthorhombic 4 simple base center, body center, face center, the monoclinic 2 simple base center, triclinic 1 simple, robohedral 1 simple, hexagonal 1 simple. In total, the 14 the Bravais lattice allowed in the 3 dimension. If you are taking any crystal system, just you can put in this 14. Or if you are making like the missing one in the cubical system is base center. If you are making base center, it will fall some other crystal system in this within this 14. Or if you are making the or tetragonal base center face center, then it will fall into some other crystal within this 14. So any crystals or any structure, it will fall within this 14. So beyond this 14 you can't categorize any crystal system in the world. So this is the Bravais lattice information we got it, we discussed it in detail, so that is a good thing. So as the end of the lecture we are going to discuss the direction and the planes in a crystal. So here, so before moving into direction and planes, we need the coordinate system to define any atomic position from the reference point. So the coordinate system or coordinates of points means locate any points in three-dimensional space as atomic position in the lattice or unit cell by constructing right-handed coordinate system. Just to look at the diagram, here we are locating that origin of the coordinate system is here. Then we have drawn the x-axis in this direction, the y-axis this direction, then z-axis this directions. So these are the right-handed coordinate system. Now you can define any atomic position in this right-handed coordinate system. Suppose if you want to define, it is residing in the plane x as well as y. It's not residing in the z. So you can tell the atomic position. Suppose if the x is like one atomic A, y is B, Z is C, then you can tell the A, comma B, comma 0, some reference with this origin. We can define with respect to the right-handed coordinate system. You can define any lattice point or atomic position. That's why we need the coordinates of point. How you can define the directions and in this figure means The crystallographic directions represent, it is defined as the line between any 2 points, or it is represented by a vector, that is the crystallographic direction. If you look at this next diagram, the each vector represents the directions in the crystallographic direction from the origin. So this direction in general, it is represented by the three numbers using this bracket. In this, if you are see this bracket in crystallographic system, means this bracket represents the vector in that particular direction. It have, because in the three right-handed coordinate system, it need the three integers. Here we are calling that integer u, v, w to represents from the origin to any direction that point. So the direction means by, it is represented by the square bracket. So that is we can call it a crystallographic direction. Anyway, we are, how you can define this UVW, anyway, that we are going to look at in the Miller indices. Right now, simply we want to know what is the crystallographic direction. That is a definition for the crystallographic direction. The last one is the crystallographic planes. These are the represented by the three Miller indices as HKL. The plane also we are going to see in the Miller indices, how you are defining the planes. Simply, plane means it's a 2D object. It's a, like a one sheet, that is a plane. See the diagram. This represents its a area, but it is diagonally along the body diagonally it is presence, but it is intersecting at three axes. So it is represented by the three number. The number are called HKL. It is called the Miller indices by this bracket. If this bracket means, it represents the direction of the crystallographic direction in the crystal. This means HKL means it's a plane number. So if HKL have a specific HKL having specific number, that represents the specific plane, that we are going to discuss in detail in the Miller indices. So this is the end of the lectures today.